Sometimes there are underlying structures or relationships between the predictor variables. For instance, new games on eBay tend to come with more Wii wheels, which may have led to the higher prices. So it may not necessarily be because the game was just new. It may be because they had more stuff with it, more wheels. So we would like to fit a model that includes all the potentially important variables simultaneously. So this would help us evaluate the relationship between the predicted variable and the outcome while controlling for the potential influence of other variables. So when I do that, when I'm looking at more than one variable, this is called multiple regression. And while we remain cautious about making any causal interpretations, this is an observational study after all, such models are a common first step in providing evidence of a causal connection. So let's go ahead and look at all the explanatory variables at once. So we want to construct a model that accounts for not only the game condition, but simultaneously account for the other three variables: stock photo, duration, and wheels. So what that means in terms of our model, now it's going to look a little more complicated. Basically, our prediction for price, we're going to base off, we still have this intercept, but we have some slope that goes with condition new. We have another slope that goes with stock photo, another slope that goes with duration, and another slope that goes with wheels. Or its most simplest way of writing it is that y hat is beta 0 plus beta 1x1 plus beta 2x2 plus beta 3x3 plus beta 4x4. So in this equation, the y represents the total price, x1 indicates whether the game was new, x2 indicates whether a stock photo was used, x3 was the duration of the auction, and x4 was the number of wheels. So just as with a single predictor case, a multiple regression model may be missing important components, or it might not precisely represent the relationship between the outcome and the available explanatory variables. And while no model is perfect, we wish to explore the possibility that this one may fit the data reasonably well. So, mostly, you're not going to be able to get perfection. You're not going to be able to do this perfectly, get absolutely perfect predictions. But let's see if fitting these four models, let's see if that helps make our predictions better. And so and by that I mean computers, we're not actually going to do this ourselves. We will estimate the parameters beta 0, beta 1, beta 2, beta 3, beta 4. We will use them the same way we did with linear regression, with the single predictor. And again, I mean computers, we will pick this betas, the B0, B1, B2, B3, B4, that minimize the sum of the squared residuals. And in this case, I'm not going to give you the formulas. They're a little beyond our class. We're just going to go with the computer output. But what's going on in the background is it's kind of the same thing we did with linear regression, where we compute a residual, square it, compute all the residuals, square all of them, add them together, and we want to fit a line this multiple regression in such a way that all those squared residuals are as small as possible. But again, we'll let the computers do that. What we will deal with is the tables. So this is an example of a multiple regression table. You notice it's just like the linear regression, only now there's more rows, more variables. There are 141 residuals for the Mario Kart data, one for each auction. We typically use a computer to minimize the sum of the squared residuals, and you see this output. So the output we read basically the same as before. When we write our equation, the equation is going to be based off this first column. So it'll be essentially your predicted price, the y hat. This would be the 3621. That's the intercept, and then I guess plus 513 for whether or not the condition is new, plus 1.08 times whatever if it's a stock photo, plus, or I guess minus 0.03 for times the number of days, so the duration, and plus 7.29 times whether or not it was the number of wheels. So that gives you a sense. I mean, we can write the equation based off that column. Next column over are the standard errors. We are not going to compute those. Just go with the values here. The next column are the test statistics. Those for each column, those are testing whether each row, the point estimate for each row, or excuse me, the parameter for each row is equal to 0 or not. And then the last one is the p-value. That's the two-tailed p-value that goes with whether or not the parameter is equal to 0 or not equal to 0. So write out the model using the point estimates below. How many predictors are there in the model? I guess we already wrote up the equation. Basically, the beta 0 is the 36.21, so 36.21 right there. Beta 1 is the 513. Beta 2 would be the $8. Beta 3 would be the negative 0.03. And beta 4 would be the 729. But anyway, in terms of the predictors, there's 1, 2, 3, 4 predictors overall. So we're using 4 different explanatory variables to predict the price. All right, so what do some of these numbers mean? What is the beta 4? That's the coefficient that goes with the wheels. So that would be this number right here is beta 4. Well, that's B4. Okay, let's go back to the question. The question is, what does beta 4, the coefficient of the variable x4, represent? Well, beta 4 would be basically how much you can expect to pay per wheel. I mean, the variable wheels are the number of wheels that are included with the auction. So beta 4 would be how much more you can expect to pay per wheel for that auction. And then in terms of the point estimate is what you get from the table. So B4 is the point estimate. But in terms of what beta 4 represents, beta 4 is basically what you can expect to pay per wheel on average. All right. So let's compute the residual for the first observation. So you can see I put the equation there, put a little bit high. But the first, so for the first observation, so keep in mind that this number right here, this is y. What we're trying to find is, using the equation, we will find y hat. And then the residual is y minus y hat. So let's write this out. It'll be 36.21 plus 513 times the condition, and the condition was a 1, so 513 plus times 1, plus 1.08 times 1, minus the last 3 days, so 0.03 times 3, and there was 1 wheel, so 729 times 1. So what do we have? Oops. There, try that again. 36.21 plus 5.13 times 1 plus 1.08 times 1 minus 0.03 times 3 plus 729 times 1. And that comes out the price of $49.62. So we would have expected $49 to pay $49.62. We actually ended up paying $51.55. So the residual would be $51.55 minus $49.62. So 51.55 minus 49.62. our residual is $1.93. That is, the actual price was $1.93 more than we predicted. And then we would do that for all the residuals. Have fun. All right, I guess I already did that. So what do the two models below have in common, and where do they differ? So these are the two models we looked at so far for this lesson. The first one was a linear regression where we only looked at condition new, and the second one was a multiple regression where I threw in 4 different variables. Well, in terms of what they have in common, looks like for both of these, condition new is significant. And well, I guess that's the main thing, is that both condition new, p-value is 0 for both of them. I mean, not quite 0, but very tiny p-value. In terms of the differences, notice that the degrees of freedom is a little bit different. That's because degrees of freedom is essentially the sample size, 141, minus the number of rows. It's 139. For this one here, we have 141 minus 1, 2, 3, 4, 5 rows. So that's why we have a degrees of freedom of 136. So degrees of freedom are a little bit different. Essentially, the more variables are used, the smaller the degrees of freedom. So there's a little bit of a trade-off. But if the variable helps, it's good they include it. If the variable doesn't help, you're better off with the degrees of freedom. And some of the other one, I guess in terms of different, obviously the second model has a lot more information. You're able to do you have more variables to make your predictions. Notice that the intercept and the condition new, the variables are different for these two. Look at these two estimates versus these two estimates. Especially for the condition new is about half what it was before, a little bit less actually. And part of that's because wheels was included. We're including wheels with the multiple regression model, but wheels was not included with the linear regression. And is actually because for the first model, linear regression, the more wheels you had, the more you would expect to pay in the auction. And that wasn't reflected in that model. Okay. So we estimated a coefficient for con nu as 1090 with a standard error of 1.26. That was for the linear regression model. Why might there be a difference between this that estimate and the one in the multiple regression setting? Again, I kind of mentioned that just a moment ago, but it's actually because of the wheels. So let's go to the answer. When we estimated the connection of the outcome price and the predictor con nu using the simple linear regression, we were unable to control for the other variables like the number of wheels included in the auction. So we say that the simple linear model was biased by the confounding variable wheels. When we use both variables, this particular underlying and unintentional bias is reduced or eliminated, though, again, there could be bias from other factors. So, this previous example about why using more variables is usually helpful. This previous example describes a common issue with multiple regression: correlation among predictive variables. We say that two predictive variables are collinear when they are correlated, and this collinearity complicates model estimation. So, while it's impossible to prevent collinearity from arising in observational data, experiments are usually designed to prevent these predictors from being collinear. So last example for this lesson. Here we go. The estimated value of the intercept was 3621. That was for the multiple regression. So here we go. That was for the multiple regression one model. Come on. There we go. So the intercept for the linear regression model was 3621. And one might be tempted to make such an interpretation of this coefficient. And where intercepts occur when your explanatory variable is 0. In multiple regression, intercepts occur when all the explanatory variables are 0. So the main thing here is that would be when the game is used. The primary image is not a stock photo. The auction duration is 0 days, and there are no Wii wheels included. Is there any value gained by making this interpretation? Well, I mean, in terms of the game being used, that's certainly a valid. That is certainly a valid interpretation. That part's good. The primary image is not a stock photo. That part seems reasonable. Duration is 0 days. That's a problem. But no Wii wheels is fine. So really, of these, the 0 days for the auction, that's a problem because none of my data included just 0 days. There's always 1 day or more. So 3 of the variables see the con new, the stock photo, wheels. 3 of the variables can take the value of 0. But the auction duration is always 1 or more days. If the auction is not up for any days, no one can bid on it. So it'd be extrapolation. So that means that the total auction price would always be 0 for such an auction. So the interpretation of the intercept is not insightful. It doesn't match any of our data.